I think you can start. Let the people in.
Yes, sir.
Yeah.
The Indian Association of Structural Engineers, also known as IAStructE, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. IAStructE is registered under the Society's Registration Act 21 of 1860. IAStructE is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IAStructE has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Kumar Ghosh, Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Alok Bhaumik, Shri Manoj Mittal and Professor R. Pradeep Kumar as its president. IAStructE is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IAStructE has collaboration with various international professional like-minded associations and institutions. IAStructe's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IAStructE endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IAStructE is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs. Seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IAStructe's activities are widely appreciated and known for quality technical contents. IAStructE is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines, and a monthly newsletter. IAStructe's publications are becoming popular with time. IAStructE has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IAStructE started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. IAStructE is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi to inculcate the professional culture and provide handholding to the budding engineers. IAStructE has its student chapters in several leading engineering institutions as well. Membership of IAStructE is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IAStructE is available on its website www.iastructe.co.in.
Vikas, my voice is audible?
Yes, sir.
Yes, yes.
Dear friends, welcome to the webinar. Today's webinar is on aerodynamics, conditions, and wind tunnel testing of cable stay bridges. The speakers are Professor Prem Krishna and Dr. Suresh Kumar. And our mentor is eminent engineer V.N. Hegde. I'll just give a briefing of our moderator. Engineer V.N. Hegde, former CEO of STRUCTE, Executive Director of Gamons, and founder of Deccan Complete Solution, has over 40 years of experience in highway, bridges, energy, marine, and hydraulic structure. He is recipient of over 16 national awards and international prize. He has over 170 publications, and he is serving on key committee of Indian Road Congress, BIS, FIB, and ICI. He is also FNEA fellow and known for his advocacy of sustainability and aesthetic in construction industries. Now, in your Hegde to proceed for further proceedings.
Yeah.
Hegde.
Thank you, Dr. Dhawan. I think hello and welcome to all the friends of IAStructE and others also who have joined this program. Very interesting program, in fact. First of all, I would like to thank Dr. Dhawan for carrying on this long innings of the tradition of carrying out one webinar per month. It used to be held physically in Delhi, but now we have switched over to the webinar mode so that not only from Delhi, all over India, the people can immensely benefit from this particular webinar series. And as I said, that we have got today two stalwarts, Professor Prem Krishna as well as Dr. Suresh Kumar. I know in their eminent engineers in the field of aerodynamics and as well as the wind engineering. Before I go to Professor Prem Krishna, I am taking the liberty to share one of the panel discussion which we are going to have in Mumbai tomorrow. That's on 26th. This is brought out. This is supported by IAStructE basically, and this is basically a sort of a brainstorming session, including the panel discussion. It's a small effort from IAStructE to support and further the cause of sustainability. It's about the steel reinforcement and steel structural members. I request all of you who have been attending this particular program, who are there from Mumbai, not to miss this. It is going to be very, very interesting. We have got very eminent panelists, as you can see on the screen. Atul Babe, Abhijit Kulkarni, Umesh Rajshirke, Anirudh Kaushal, Mukesh Pitam Dasani and Abhay Bombale. They're all from the western region of IAStructE. And I assure you, it's going to be very interesting. And we'll be discussing a lot about the stainless steel reinforcement as well as the stainless steel structural steel. Those who are not registered yet, there are still some opportunity for registration. Don't miss it. And this is a free registration. And I expect people to come and join this particular the panel discussion which we are going to have. Now, with that, I would like to come to today's business, and we have got, as I said, that Professor Prem Krishna will be making his first presentation, followed up by Dr. Suresh Kumar, and I will have the introduction of Professor Prem Krishna first, and after his presentation, we will be taking it up. The other speaker also, and they'll be talking for half an hour each, roughly, and we'll take the question and answer at the end of this presentations by both of them. And just to introduce our first speaker, Professor Prem Krishna, I would like to address him in the first person. Professor Prem Krishna, you have been the doyen of a sort of a civil engineering, including the wind engineering. You are not just confined to the wind engineering, and I can call you a Bhishma Pitama of wind engineering as well as the long span bridges conception. In fact, I've been interacting with you for a long time as far as the long span bridges is concerned. Professor Prem Krishna was the president of the International Wind Engineering Association, and also perhaps, if I'm not mistaken, he's responsible for setting up the first wind tunnel testing facility in IIT Roorkee, and his professional interest not only includes long span cable routes and bridge structures, but as said, the main interest is always in the wind engineering. He's responsible, I think he's responsible for the conception and the design of one of the first cable supported bridges in India, that is in Haridwar. And your interaction, Professor Prem Krishna, has been with us, especially as a head of the Civil Infrastructure Committee of INE, Indian National Academy of Engineering, which is the apex body of professional engineers of the country, in my opinion, has been very, very interesting. You have been a very pleasant personality also, apart from being an eminent professional engineer. And we are all here to, to the treatise today from you on the aerodynamics and wind tunnel testing of the structures. I'm not just putting it as a, like cable supported structures, because you have been involved in the roof structures too. I know that you have been involved in the wind tunnel testings. Particularly, I'm very, proud that you were involved in the wind tunnel testing of the, what I call it as a national Namaste signature bridge. That was there in Delhi, where I was also involved to a large extent. My interaction with you have been always, like I should say, it is reminiscing for me particularly, whether it was a Chenab Bridge interaction during its conception stage, or the Anjikad Bridge conception during its conception stage. So your personality, your knowledge, Professor Prem Krishna, we are all in awe with, and the virtual podium is yours, and you'll have to take and I request you to treat us with your treatise. I think you can just share your presentation to start with.
Well, good afternoon to all of you. I hope you can hear me.
Yes, we can.
Thank you so much, Mr. Hegde. Mr. Hegde himself is such a brilliant engineer. He was introduced to you. But not only that, he has mastered engineering in many aspects of it. He has also mastered the art of introducing people.
Yes.
The kindness with which he has introduced me is quite outstanding, and I'm very thankful to him. When somebody calls you a Bhishma Pitama, you get an idea of how old you are. And I don't deny that age as well.
By the way, just to continue with that, I think when you did your doctorate from Imperial College of London, I was just 2 years old, but I'm a senior citizen now. That shows why you are a Bhishma Pitama.
Okay, thank you so much. Friends, as you have just learned from Mr. Hegde, this is a twin presentation. I'll be speaking first and then Dr. Suresh. In my part, I'm only touching upon some salient features about wind in general, what kind of loading it imposes on structures, how we generally design structures for wind, and then come to certain features of the aerodynamic effects of wind on cable stayed bridges. And mine are kind of preliminary introductions on all these aspects. The real exciting part will come when Dr. Suresh will share with you he will elaborate on some of the things that I mentioned, and he will also, give you some very interesting information about the wind tunnel testing of cable stayed bridge models. So let me begin. Yeah.
Yes.
I think that part has been taken care of by Mr. Hegde already. So I go to the next slide. Well, wind generation is something which occurs over the sea mainly, particularly as far as cyclones and hurricanes are concerned. Of course, there are also inland storms, as I've listed here. All kinds of storms I've listed. Gales and monsoonic winds, and localized storms and cyclonic winds. Tornadoes are, inland development, and thunderstorms. By and large, of course, as far as India is concerned, we are affected by gales and monsoonic winds, localized storms, of course, dust storms, cyclones. Tornadoes and thunderstorms are comparatively much less of an activity on the Indian subcontinent. So that's generally the various kinds of windstorms that we have. And as I said, of concern to us more are the first three types. Just a picture of a cyclonic storm. The special thing to note in this, let me get a, where are we? Yeah. The main feature of a cyclonic storm, which we must remember, is its circulatory motion as it moves from sea towards the land. You can notice that also very clearly in this picture. This is special about cyclones. Then you have a tornado, which I've called a narrow band phenomena, which is more or less, as I said, an inland phenomena. The difference between this also has circulatory motion of wind. The difference between a cyclone and a tornado, very broadly, will be that a cyclone is a wide band activity. It can cover an area of 800 to 1,000 kilometers at a time, whereas a tornado is a few hundred kilometers, if at all. And so it's a narrow band activity. Also, it doesn't travel very much, whereas a cyclone has a much wider coverage. And that is why it is of so much concern as far as the destructive capacity of a windstorm is concerned. Then we have a picture here of a thunderstorm. Again, something which occurs off and on, but it's not a very common phenomena which we take into account for design purposes. On this slide, you will see a trace of wind velocity, which is my patent picture. I've been showing it again and again. that if you measure wind velocity at a certain point, this is the kind of trace that you get, fluctuating up and down, above and below a mean line. So it's a fluctuating phenomena that wind velocity is. And if you look at the variation of wind velocity from ground upwards, then you get a mean like this, as shown here, and above, up and down below this mean is of course a fluctuating component. But mainly I'm showing this figure to show that this is the way it grows from the ground towards a certain height here, which we call the gradient height. The gradient height will vary and it will depend upon the type of approach terrain that you have. It may be 200 meters above ground, or it can go up to 500 meters. The design of structures for wind effects is based on boundary layer flow, which is deemed to cover cyclonic storms as well, but not tornadoes and thunderstorms, which have a somewhat different structure as far as wind flow is concerned. And this is not so much of a concern for us because we, in any case, don't design structures for tornadoes and even thunderstorms. So, except perhaps some very special structures, like in the nuclear power plants, some components may be designed for very high speeds, which a tornado unleashes. Also, I may mention here, in tornadoes, the wind speeds are even higher than in cyclones. So, thunderstorm that way is, if it strikes you, it is going to be something which is lethal, but fortunately, it is not so common. So, as you have noticed from that graph there, wind is a natural randomly varying dynamic phenomena which evokes a dynamic response from any structure, big or small, when it obstructs the flow of wind. The only difference is that for stocky structures, the dynamic component is small and it may even be negligible. And therefore, you can go for a quasi-static design approach for stocky structures, small in height and wide coverage. The more flexible, longer span structures, such as the ones that we are dealing with today, cable bridges. And depending upon their span, these structures will exhibit dynamic response, and this dynamic response is substantial. And such structures are termed as wind-sensitive structures. So you have two types, which are stocky structures, which will exhibit much smaller aerodynamic response. And then you have the wind-sensitive structures, which have a predominantly aerodynamic response, which we have to take care of. In general, this is a very simple equation that we see here. The force due to wind is obtained as a coefficient C multiplied by the pressure multiplied by the area on which the wind is impinging. P is equal to half rho v squared. Rho is the mass density of air. V is the velocity that with which the wind is impinging on the structure. And this is something which we can get from the Indian Standard 875. The values of wind velocity for different zones in the country are specified in the Indian Standard 875. C, as I said, is a coefficient. It can be a pressure coefficient, it can be a drag, it can be a moment coefficient, and so on and so forth. For a quasi-static assessment, the value of V that is adopted is the 3-second average velocity, which means that the average of velocity, you notice that fluctuating trace of wind. And in that, if you take a 3-second time span and you average it over 3 seconds, then that will be called the 3-second average. And statistically, a value of the 3-second average wind is worked out and specified in the codal provisions. For dynamic assessments, we used is quite commonly the mean hourly average wind, and the force that you get is then multiplied by a gust factor G. So there is a somewhat different approach when you deal with these wind-sensitive structures. You have the mean hourly wind as the basis in this expression here, and you multiply the result with the gust factor G. So this is the simple way in which you can tackle wind loading on structures. Of course, one would say that this is a deceptively simple equation, because what is the challenge? The challenge is to know these appropriate coefficients that we are talking about. That's something which people have to research on to get those values. Have been researching on for almost 100 years for different kinds of situations to get the value of this coefficient C. And then to be able to define the wind velocity also, because it's such a variable phenomena, wind is, that it's not such a simple thing to get at the value of V. That is, those are the issues where the challenge lies in using this simple equation that we've got here. The design of cable bridges is an iterative process, just like any other structure. You know that. You assume certain sizes, you assume certain forces. In fact, on that basis, if you have the sizes, then you can estimate the forces. Forces are specified. And then when you design the structure, there may be need to revise the design. So this is the process of any kind of structural design that I'm mentioning in a general way. So can I get, what happened there?
What exactly you want, Professor?
I think I'm seeing your screen. It has come in front of my slides.
My screen. I have not shared anything. No. So, you can request multiple presenter to share. I think no. Replace.
Also, I think you can go to the view option. Maybe you have chosen some other view, or it has changed.
Yeah.
My screen has come.
Yeah, I see you.
No. I think you have my screen in the sense. I think you have to swap there. I think where you go there, and
We are able to see your PPT, by the way.
yes.
PPT is visible.
Oh,
No. What is
I can't see my people.
No. Wherever you are,
I think you can stop sharing and share again. Maybe.
No. What has happened? I think you just go to your wherever you are.
No, I think I do that. I stop share and share again.
Okay.
Yes, that would be better.
Oh, yes. Thank you. I don't know what I pressed. This is what, the Bhishma Pitamas do, Yeah. Okay. So this is just a general statement about how we go about designing structures, and cable stayed bridges are not an exception.
Yeah.
The design of cable stayed bridges, yes. Okay. Oh.
Again, it happened.
Now the slide is not moving.
You click on that slide. You click on the slide first, and after that you move it. Click on the slide and After that, you move it.
Yeah, now it's moving.
Yes.
Yeah. The main code for wind loading for all structures is the BIS standard, as I mentioned earlier also, the Indian Standard 875 Part 3, 2015 version, which is we are now trying to revise, from which the basic wind parameters are taken. The wind-related design can then be carried out with the help of dedicated codes for different structures, such as the IS 875 for buildings, IRC 6 for bridges in general, and IRC 136 for CSBs, cable stayed bridges, and 137 for extra dose bridges. The wind-related analysis or design of cable stayed bridges can be best addressed in terms of their three main elements, namely towers, cables, and deck. So I come to from this general description of wind and how it affects structures and how IS 875 helps us in getting the values of wind velocities, etc., and other parameters. Now I come to cable stayed bridges itself. And how much time have I got? Yeah, okay. Towers first. Wind effects on towers can generally be treated akin to any tower, tall tower, as per the provisions of IS 875 Part 3. For short or stocky towers, satisfying the conditions given below, height upon lateral dimension less than 5, and frequency of vibration more than 1 Hz. A quasi-static approach is followed. And you saw that equation which I shared with you earlier that can be used. The various kinds of coefficients can be found in the code. Taller towers experience aerodynamic oscillations, which can occur in the along wind as well as the across wind direction. We have a picture here that will indicate that. Yeah, you can see this. If wind is blowing in this direction, then this is a crosswind oscillation occurring here. And this is the along wind response. The along wind response for towers, chimneys, and structures like that is monotonic in one direction, and the across wind oscillations are across the axis of the structure. So this is how this oscillates, and both can be very important for the design of the tall structure. So this is something which I'm mentioning is common to any kind of tall structure that you're dealing with. Then we come to cable stays, which are special to cable stayed bridges. The dynamic response for along is computed on the basis of the mean hourly wind velocity and is multiplied by the gust factor G using formulations given in IS 875. The dynamic response for the crosswind direction is computed by using formulations again given likewise in IS 875. It is noteworthy that towers in cable stayed bridges particularly should be examined for their safety against wind at different stages of construction. This is something very important, that a cable stayed bridge, being a long span, flexible structure, as it goes through the various steps of construction, has to be examined for its safety against wind, both static as well as aerodynamic. Now, wind-induced cable vibrations. If it were a matter of a short cable, of course, you can again go back to that same basic equation and compute the force on the cable. But if it is one of the longer stays, like in cable stayed bridges, the stays can be pretty long. Just to share a figure with you, suppose you have a 1,000-meter span cable stayed bridge. The length of the cable could be as long as 600 meters. So imagine the length of the cable. So it's like a thin string there, and will certainly experience aerodynamic oscillations. The various kinds of oscillations that can occur I've shown here on the slide. You have this stay vibrating like this. Then if you often, in design of cable stayed bridges, you do sometimes use two smaller cables rather than one big cable. And if these cables are placed in the fashion that they're shown in this figure, then these can experience wake vibrations. This is the cable which is in the wake of the windward cable. And this cable can experience wake vibrations. Also, vibrations can occur in cables due to a combination of rain and certain wind speeds. So, wind, the water is flowing here in this on the cross section of the cable, and at certain speeds, this can undergo vibrations because of the combination of this rain and wind. Let us just see certain more stipulations about this. For short cables, I have repeated the equation that I've used above, only except to say that the drag coefficient, that appropriate coefficient we were talking about, C, is here the drag coefficient, and the value of this drag coefficient is between 0.7 and 0.8. Now, for longer cables, as I've just mentioned, we used is the mean hourly average with the force multiplied by a gust factor G, and the order of that gust factor is 1.2. So that is how you can compute the forces on a cable due to wind. Now, rain-wind oscillations occur when typically the frequency of vibration of the cable is between 1 and 3 Hertz. The wind speed is between 3 and 18 meters per second. The angle of incidence is 30 to 80 degrees from perpendicular to the cable. So these are the given broadly the guidelines of the frequency of vibration, the speed, and the angle of incidence. And if these are satisfied, then you will expect to get rain-wind oscillations. Rain-wind oscillations can be avoided if the Scruton number is greater than 10 for smooth surfaces and is greater than 5 for textured surfaces. Sometimes these the surfaces of the cable are textured. And in that case, if the Scruton number is greater than 5, then you do not expect to get rain-wind oscillations. It is advised in the the IRC 136 that cables longer than 80 meters should normally be checked for the possibility of rain-wind oscillations. Wake galloping, like the one I've shown in the slide there, when the distance between the cables is between 2 to 5 times the diameter, it is likely to occur. And if the distance is not in this range, then it is unlikely to occur. So that's the wake galloping. Now we come to the deck. And if I may say so, and I think Dr. Suresh will also emphasize this in great detail, that the aerodynamics of the deck in these long span bridges, the cable stayed bridge types, is perhaps the most important aerodynamic phenomena for cable bridges. And it is there that much of the attention is given to ensure that the bridge will remain within safe limits as far as aerodynamic effects are concerned. It is not that you ignore cables and towers, I'm not saying that, but the deck is perhaps the more important element of a cable stayed bridge, which has to be examined from this point of view. The bridge deck, perhaps the most, as I said here, the three prominent modes of vibration of deck: vertical, transverse, and torsional. Often also in cable stayed bridges, the frequency of vibration or the frequencies of vibration can be very closely spaced. And coupling of flexural and torsional modes of vibration, if they are close to each other, can lead to the possibility of flutter. And in examining decks for aerodynamic stability, flutter is something which is a very important word. It has to be, you have to avoid it like you avoid taking poison. Vibration characteristics, it's also, as I mentioned earlier also, that vibration characteristics change with the construction stages. And therefore, the checking on the stability of the bridge from the wind point of view has to be done at different stages. Wind forces on a typical bridge deck, these equations are given here. The drag, the lift, this is drag, and this is the torsional moment. And this is the simple equation, which is more or less a repeat of what I've written earlier slides. Here, for a deck, the value of the variation of drag is given. This is how CD varies with the angle of incidence. This is the angle of incidence alpha W. So as this changes, the value of drag or lift or moment coefficient also changes. And the variation is given here. The minus 10 degrees to plus 10 here varies almost 0.85 to minus 0.85 to about 0.8 here. Torsional moment about minus 2 to about plus 0.2. The drag about 0.2. This is the variation. This is for a typical case. Don't say that the variation is going to take place on all kinds of decks. This is for a typical case. Also, and this is something which again, I'm sure Dr. Suresh is going to explain to you in detail. If the wind is blowing against a bridge deck here as shown, then within different speed ranges, different kinds of oscillations can occur. At lower speeds, you get what you call vortex-induced oscillations. This is the range when buffeting is important, and this is the range where flutter or galloping becomes important. And this is the stage which is of greater concern for us as bridge engineers as we examine bridges for aerodynamic safety. Now, there are, Mr. Hegde, how many minutes?
How many minutes you want?
Maybe 5.
5. Okay, fine. Please,
Okay.
please go ahead.
Right.
I will request Dr. Suresh Kumar to stay back for 5 more minutes.
Okay. Okay. Yeah, there are sensitivity checks which you can apply to a bridge in order to see whether it is going to be aerodynamically unstable in any way or it is a stable structure. And I'll not stay on this slide. These are given, this is a repeat from the IRC 136 that we just talked about. So with this, you can broadly, in the initial stages itself, get an idea whether your bridge is going to be aerodynamic sensitive or not going to be sensitive. And if it is going to be sensitive, yes, then you have to take investigative measures and remedial measures. Most cable bridges are unlikely to pass this test unless these are of very small span, say 150 meters. This 150 meters is just a hunch. It's not a magic figure. And in any case, you're going to apply those checks. And that is what will tell you whether the bridge is as being a dividing line. But as I said, that's not from the Bible. If the possibility of aerodynamic actions is indicated, you carry out a dynamic analysis of the bridge, if perhaps you have not carried out already. Vortex-induced vibration amplitudes, flutter speeds, etc. can be computed at this stage using IRC 136. And design modifications can be introduced at this stage also, if necessary, to make the design more acceptable aerodynamically. So that's the first stage. Then you have these equations, which I think Dr. Suresh will be talking about. From this, if it is stipulated that if this parameter PB is between a certain range, the bridge is prone to aerodynamic oscillations. If it is greater than 1, then the bridge is highly susceptible to aerodynamic oscillations. And it means that if it is less than 0.04, it is not susceptible. Also, another method is given, and this is another one that is given. And this also says that the bridge components are deemed wind sensitive when the mass damping parameter SW is less than 1. So these two empirical expressions can give you an idea of what to expect as far as the aerodynamics of the bridge is concerned. Now the IRC 136 says that even if one of the above parameters indicates aerodynamic sensitivity, then further investigations have got to be pursued. Furthermore, it specifies that whether or not whatever value you get from those equations, if the span of the cable stayed bridge is more than 250 meters, then aerodynamic investigations, including wind tunnel testing, should be carried out. That is what is specified in the code. Also, if a bridge site is windy, such as locations in the coast of India or the hilly regions where deep valleys can experience accentuation of wind speed, it will be prudent to carry out a wind climate assessment, which will provide more detailed information on the wind climate around the bridge site. The project should, in such cases, consider aerodynamic investigations, including a wind tunnel study, even for spans less than 250 meters. What the intention is not to err on the wrong side. If you have to err or do more effort, you go to the safer side. And yes, within those 5 minutes, I have completed. Thank you very much for giving me your patience and to listen to me. And I think now next, this very exciting part of the program today follows from Dr. Suresh. Over to Mr. Hegde.
Thank you. Thank you, Professor Prem Krishna. I've been hearing you so many times on this wind engineering. Every time I hear you, my fundamentals on the engineering gets clearer, like it becomes clear, whether it's a flutter, whether it's an oscillation, whether it's across the wind oscillation, vortex shedding, everything gets cleared. And there are a couple of questions, as you can see in the question and answer box. I think we'll take it live rather than answering online. I think let us have a discussion on that at the end of the session. With this, I wholeheartedly thank you for that wonderful presentation. And another wonderful presentation we are going to come now. Dr. K. Suresh Kumar is with us. He's another very eminent engineer. As I introduced Professor Prem Krishna in first person, I would like to introduce Dr. Suresh Kumar too. Dr. Suresh Kumar, you have moved over to Dubai now, and from India, you have been stationed over there, and you have more than 35 years of experience, not only nationally but internationally too in wind engineering, and you have established, I think, the fifth RDWDI wind tunnel testing facility in Trivandrum, and after having successfully run it, now you have shifted over to Dubai. I again, recall my sort of interaction with Dr. K. Suresh Kumar when we were doing the wind tunnel testing for Anjikar Bridge, but unfortunately that bridge had to be stopped in between. Later, it was done by HCC. This Anjikad particular railway bridge I'm talking about, a wonderful bridge which was constructed by HCC later. But earlier, it was a bridge similar to that of the Chana Bridge. It was a trussed arch bridge of 250 meters span in the gorge, and for that we had a very lively interaction with you, Dr. Suresh Kumar, and if you recall, we had written a paper together for that particular Anjikad wind tunnel testing. And also you were involved in the world's tallest, almost 1 kilometer tall Burj Khalifa in Dubai. Now I understand from you, you have been involved in the wind tunnel testing of the tallest tower, which is under construction in Jeddah. I think you said it's a King's Tower, perhaps. And you have been also involved in so many research papers, and you are not new to our audience, by the way. You know, like we are very familiar with you, and we are here to, hear you once again for your wonderful, presentation. I'm sure the people are going to be treated with your presentation as Dr. Prem Krishna, mentioned it. Suresh Kumar, it's all yours.
Thank you. Thanks, everybody. I hope you can hear me.
Yeah.
And thanks for the kind introduction and remembering our days for Anjikad Bridge, which is long back. And also it's a great honor to present after Professor Prem Krishna. He's the one who asked me whether I can join with him. So why not? I mean, wholeheartedly I agreed. So let me open my presentation. I'm going to be quick probably, but let me see. You can see.
Yes, we can see. You can go to the.
Yeah.
You can go to the presentation mode.
Yeah. Yeah.
It's not gone yet. Yeah. Perfect.
Yes. Okay. So I'm talking mostly on section model studies on long-span bridges. I'm not going to be talking about elastic modeling or anything like that. This is a fundamental test. I thought probably this is the one, the best to talk about in this forum. So before I do, I just want to show you why we are doing such testing. A few videos. You can see one of them very familiar. Might have seen it already a number of times. That's a flutter which is happening on the Tackman Arrows. The other one is another bridge in, I forgot the name of it, it's in Russia, which is undergoing vortex-induced oscillations. The last video is showing the testing. While we are doing the testing, some oscillations are happening. So basically, all I can say is those who are in wind engineering, all I can say is that bridges are quite different compared to tall buildings. Okay, this is whatever you see or experience on bridges is not going to happen in tall buildings. So I'm not going to get into that today, why tall buildings are not subjected to such unstable motions. When to consider wind study, I think Professor Prem Krishna already covered, so I'm not going to be talking too much on this as well. Basically, footbridges spanning more than 60 meters, highway bridges more than 100 meters are typically being tested. Then fundamental period higher than 1 second and things like that. But there is no clear cut. I mean, you can't say it's not written in stone. I mean, there are reasons sometimes you may avoid some testing as well. So best is to consult with a specialist so that you can do some planning right from the beginning. So the essential in wind engineering studies, I thought this is something which you cannot avoid actually. Okay, when you are doing bridges, some of these things you cannot avoid. So one is wind climate analysis. When especially you are in a hilly terrain or something, you need to know what is the speed at which the bridge should be designed, which is not very clear from the codes. So you need to be paying some attention to this. Maybe your speed is higher or your speed can be lower. I think in Anjikad Bridge, I vividly remember our speed was higher than what is in the code.
Yes.
So you need to be careful with the effects of topography on wind speeds. The second thing is you need to do at least a desktop stability assessment, because you need to make sure that your bridge is going to be stable, stable for vortex shedding and galloping and even flutter. If in case you're doubtful, then you go move into section model test to confirm it. You need to verify. And if there is a problem, then you need to have mitigation measures. I'll be showing some of those today. And then lastly, buffeting analysis. Buffeting analysis will utilize some of the stuff which we are getting from section model test, and then do the analytical simulations to get the responses and load distributions, because that's what is required ultimately for the design of the bridge. So here you go, section model test. So in section model test, like I said, there are some criteria you have to be looking into, like flutter. I'm using IAStructE criteria here. I think most of you are working in bridges will be knowing. For construction, you need to pass beyond 1,000-year return period speed. And for completed stage, you have to be passing beyond 10,000-year return period speed, which looks awfully higher speed. But I think Prof. Prem Krishna already discussed that you don't want to be having any issue to your bridge, because if flutter comes into the picture, then it will basically break the bridge. So that's why the return period is set very high, so that there's no chance that this speed is going to occur and your bridge is going to be stable. But you're not designing for 10,000 year, you're designing for 100 year, or even some ultimate limit state design, maybe 1,700 year return period maximum. Then in vortex shedding too, there are criteria. So you need to be within certain acceleration limits. So up to 13 meters per second, you should be within 5% gravity. Then up to 22 meters per second, you have to be within 10% gravity. So these are criteria already set between quotes. These particular ones, I'm picking it from IAStructE. So if these things are happening beyond 22 meters per second, then it's not anymore a comfort issue. It's more of a strength or fatigue issue. So that needs to be treated separately. So what is this section model test? Section model test is basically a pass or fail test. That's what in simple terms you can say. Either you'll pass or you'll fail. So this is carried out at the preliminary stage. You are assessing basically the deck section. The deck is stable or not. And what you're trying to look at it, you're trying to look at the flutter, vortex shedding, have return buffering, but you're not really looking at buffering. You're looking at basically flutter, even galloping or vortex shedding. In case of stability issue, then you have to look into remedial measures. There are easy way to change the shape of the bridge so that you can make it stable. So at this point, damping is not at all being considered at this stage, because if there is a problem, you will straight away look into the shape of the bridge rather than damping. But I know certain bridges, after remedial measures have been found out, still the structural engineers prefer to go into damping, because they thought that that is probably easier to do it rather than doing change the shape of the bridge. However, you need sometimes a redundant system for damping. Other things that you will get out of it is static coefficients and aerodynamic derivatives. So typically you'll pick a section of the bridge. You won't test the entire bridge. You'll pick only a section of the bridge which will be around 100 meters or 120 meters. In case of non-uniform decks, this is something to be discussed. Which section you wanted to test. Sometimes you may have to test multiple sections in non-uniform deck sections. But most of the bridges are long span ones are quite uniform, so you can pick as most of the time center section. This is a rigid test, geometrically representing, basically this is representing the full scale deck, a portion of the full scale deck. The scale is approximately 1:30 to 1:80. Materials used, brass, aluminum, wood, plexiglass. Nowadays 3D printing, okay, before there was no 3D printers. So we used to build everything by hand. So you can see some of the bridges that I'm showing here. Just a minute. This one is a bridge. You can see how detailed we do the modeling. This is sometimes looks silly because you may think that, oh, this is underside of the bridge. Probably we can skip some of these things, but you shouldn't be, because wind is going to be seeing all of these things, and the water shedding above the deck and underneath the deck is going to be interacting. So all of these elements could be of use. So you can see the cape raising and the rest of the elements underneath this particular bridge, everything built using balsa wood in this case. So it's a quite heavy process. But now if we do this, likely this will all get printed using 3D printers. And as far as the modeling is concerned, geometric similarity, kinematic similarity, and dynamic similarity has to be followed. And this is not float number scaling, okay? This is simply LVT scaling. You can scale the length, velocity, and time separately in this particular case, which is a very high advantage compared to float scaling, because float number scaling, you had to do it in aeroelastic test, not in section model test. So you can do this, depending on the size of your tunnel and etc., you have to fix it, because the tunnel might have a particular velocity up to which you can do the test. So then you know the full scale velocity from which you can get the velocity scale. You have the length scale, then you can get the time scale. From time scale, you can get the frequency scale, etc. And the damping needs to be exactly the same. So you can, nowadays we are doing the damping using magnetic dampers. So the frequency is simulated using springs. So I'm just showing you one of the box cutter bridge where you can see what is going on. This is these are the modes we have selected. Typically, you'll select the first vertical mode and the torsional mode, adjacent torsional mode. And then I'm just showing the key parameters in the section model full scale versus 1:6C model of what we simulated. The vertical frequency, what is in the full scale versus actual, and etc. What is important is the frequency ratio. That torsional to vertical should be the same both in model scale and full scale. So here the ratio is 2.87. That has been simulated. And if you look at the deck mass, this deck is around 15.4 kilos. So it can be fairly heavy. And the deck mass moment of inertia has to be simulated as well. Vertical damping around 0.25% and 0.3% torsion damping. This is the response we got. We are plotting peak vertical deflection versus the peak torsional deflection. You can see there is a blip at a very low speed. There is a vortex shedding. However, still it is within 5% of G. So it is not a great concern. However, the deflection is quite huge, like 0.5 meters. So this is a very long span bridge. So this is not a good deflection for a span of about a kilometer. So we asked them to relook at the shape again. But when you look at the peak torsion deflection, you can see there is no blip. So it is all clear within 5% G. But there is a flutter happening, but the flutter is happening after the flutter criterion. So it is not a concern because this is passing the 10,000 year criterion. So you can allow that. I mean, you have to look at up to 10,000 year return period. Beyond that, you can get into flutter. If you have any issues, you look for changing shape. Like I said before, end fairing to make it more aerodynamic, like triangle pieces attached to the bridge. And then you can also have baffled plates underneath so that it will disturb the vortex shedding, which is happening above versus what is happening underneath. So with these techniques, you can bring down these exceedances above certain criteria, 5% G, 10% G, sometimes it will exceed. So you can bring it down using these simple techniques. And this can be found out at the time of the test. Okay, when you do the test, you can attach these elements and you can prove it, that it is within the limits. You can also use gate vanes. You can see this little piece at the edges, which will basically deflect the flow. It will allow the flow to go through the bridge and the gate vane in between, and also it is outside, so that basically you are disturbing the vortex shedding coming out to that edge. So you can use simple techniques like this. We have used it, and I'm going to show some of those examples. This is a bridge in India, which we have done. This is a double deck, side by side. We have tested. This is not tested in India, tested abroad in Canada. So you can see again inside what is going on. There's a lot of details. So you have to be simulating everything exactly according to the scale. So you cannot avoid anything, including the parapet. Okay, whatever the porosity of the parapet, that needs to be simulated as well. This is a fancy rig system because you have to hang this bridge on a spring system. So you'll have vertical springs and you have torsional springs. Both of them will create the torsional frequency and the vertical frequency, and also the ratio that you're looking for. And then the measurements will be taken outside of the tunnel. So you'll have a laser system pointed to pointers so that you know the motion of the bridge on either side of it. So you have all kinds of measurements which can be done on this bridge. I have a few videos. You'll be interested to see some of these. This bridge had some trouble. So one is the vertical vibration, and also you can see the torsional issues. As if it looks like we are trying to vibrate it forcefully, but we are not doing anything. The wind is doing the job. But when you change the speed, it will go to no oscillation. So it is purely vortex shedding. This is not a flutter issue. If it would have been a flutter issue, we would have stopped the test by now because it will fail the model. Okay, so you need to know where your flutter you're expecting and where you're expecting your vortex shedding. You can do some calculation in advance. So you are expecting certain thing at a particular speed. This is another bridge in India we have done. So here again, I mean, it's a very, it's a long span bridge, not really long span, 75-meter span, but there are a number of 75 meters. So in total, it's about 1.2 kilometer bridge. So this bridge had some issues as well, vertical vibration. And then we had to put gate vanes underneath it to arrest the motions. At the beginning, we have done some, safety simulation to see whether this gate vane is going to be helpful. You can see there are large vortices here on the left side, and on the right side, those vortices are broken. So we know that this is going to work. So after seeing this, we have done the test. So during the test, you can see what is going on. So these are very large spikes happen, peak vertical deflection. And then with the use of that change mitigation, we could reduce the response significantly. Those are the red ones. There is no spike at all. So that one you can see here. This is the vibration we have noticed in that particular bridge. You can see again, this is hung on springs and simulating whatever we have been looking for. And then finally, if you look at this gate vane with this diagram, underneath the bridge, we could able to bring this oscillation down significantly and within limits. In fact, there is no torsion oscillation. Torsion is within limit. There is no flutter issue on this bridge. So it's all about vortex shedding. So we also got force and moment coefficient, which I think Professor Prem Krishna already covered. So I don't have to talk about this. This is a very important information you'll get out of section model test. And this should be used for your buffeting analysis to get the loads on the cables and decks and etc. This is primarily deck. However, for when you do buffeting, you have to do for cables as well as for towers. You'll also get aerodynamic derivatives. When you talk about force and moment coefficient, this is primarily static stuff. And when you get into dynamics, you can get aerodynamic derivatives. This is primarily when you are blowing wind and the bridge is in motion. Its stiffness as well as damping can get changed depending on the speed. So this is talking about system damping and system stiffness according to the reduced velocity or reduced frequency. So if it is going, there are 8 derivatives, H1 to H4 star and A1 to A4 star. When the derivative is going negative direction, this is going to give you positive aerodynamic damping. When it is going above, then that is going to give you negative aerodynamic damping as well as negative stiffness. Negative stiffness means your stiffness is taking away when the wind is blowing against the bridge. So these are very important information which we will get out of the section model test. And this will be utilized when we were doing the buffeting analysis. Another bridge again from India, and this is quite a wider bridge. This also had some motion issues. I'm not naming the bridge because I didn't bother getting permissions from various vendors. So I'm just showing without the naming. So you can see the oscillations. Okay, finally, we are able to solve this issue using solid middle barrier. You can see the middle barrier was a little at the beginning, but we asked them to increase the middle barrier to 1.6 meter. Plus, we also use the baffle plates underneath. Through these two things, we could able to solve the problem. And then again, this will be confirmed through the test. We cannot just say that this will work and just leave it. We have to confirm it through the test, and that's what we have done. You can see the vertical VIO, and mitigated one is the red line. There's nothing there through that middle barrier as well as the baffle plate. And then you can also see there's a torsion VIO. Even though it is not exceeding the criteria, it is quite large. So through these mitigation measures, we are able to bring it down. So these are wonders one can do when you change the shape of the bridge. At the beginning, you may not be knowing whether it is really required or not. However, the rule of thumb is when your deck section is very blunt, likely you are going to get all of these issues. Okay, because most of the bridge I am seeing nowadays blunt shape, right at the edge, there's a girder, large girder, blunt. And then this can happen. Likely it is going to be happening. And that's what happened in some of these bridges. In certain cases, even if it is aerodynamically nice at the beginning, the one which I showed, the second one, if you look at it, it looks like nice shape. However, it had some issues too, so that we had to use the gate vane underneath the bridge to get rid of this water shedding issue. And none of these bridges having any flutter issue, fortunately. So you can see it is going flat, almost flat, very high speed. Flutter is expected to have at very high speed. Like I said before, we check up to 10,000 year return period speed, and if it is passing, then the bridge is passed. You can see some of the interesting designs we have done. I mean, these are dedicated modeling. Okay, like I said before, the weight needs to be matched, the stiffness through the springs, the weight and the shape through the actual model. Okay, likely. And then the springs are going to give you basically the stiffness and the damping using magnetic dampers. And then together it will work as a section model. You can see some of these equipments which we are using. These are quite significant systems we have developed where you have vertical springs, horizontal springs, and also you have damping system and all the measurement system, including lasers and etc. So this is at the outside of the tunnel section, which is sitting outside, and the deck will be inside the tunnel. This is an interesting project. I think this we have done after, this is the Golden Gate Bridge, okay, in San Francisco. You might be wondering, this bridge is already built 1940s, and recently it came for a test. The reason is they wanted to assemble a suicide barrier. They wanted to install a suicide barrier, and then the aerodynamics of the bridge got changed. So, like I said, I mean, any small thing that you do to some sensitive bridges, this can change the aerodynamics significantly. So one should be very careful. It's not like in a building. Sometimes, they put a board and things like that on a building. On a building, it is fine, but it's not fine for a bridge. Bridge will have an issue as far as aerodynamics is concerned. So you can see this is the Golden Gate Bridge. When we tested, we found out some interesting motions. These are some of the modes that we were looking at, mode 2.086 and mode 7.189. So at any point that you wanted to change a section of the bridge, you had to take a cautious approach. Recently, I'm hearing some incidents from India as well, which I'm not going to be sharing here because of confidential purpose. And exactly the same thing happened. Without consulting, they tried to change the shape of the bridge. And now I'm hearing there are some oscillations. So we have to deal with that right now, how to get rid of those oscillations. And sometimes the bridges are tested, including the traffic on the bridge, and this can change the aerodynamics completely. This particular test, I think we have been doing near the border. So at the border of Canada and US, there's a bridge where the traffic at times is quite heavy. And at the same time, when you are getting very high wind also, you can have some problems. So that's why we looked at these cases separately. What is going to be happening to the stability of the bridge, including the traffic. The traffic is almost dead because this is immigration right after this, so everybody is on a queue to pass. At the same time, the storm can happen, especially in Canada. There are winter storms, so it can happen at any given point. And so this, testing two deck sections at the same time is a very important test, because sometimes you may think that, okay, I can make one bridge kind of a dead, it's like a dummy model, not moving. The other bridge is like a moving model, which is not a good idea, because there are something called aerodynamic coupling between the two. In order to have the aerodynamic coupling, I think both models should be moving. So we have a facility where we can do two models at the same time. We can have different separations as well. You can have, I don't know what is the extent we can go, but however, a normal extent of the gap can be maintained, like 20 meters, 50 meters can be maintained, and we can study about the aerodynamic coupling between the motion of the bridges. So I think these are what I would say is the basic tests that one should be doing. If your desktop assessment is saying that the bridge is going to have some trouble. So in such cases, you need to prove it that the bridge is going to be stable. And if it is not stable, you have to assemble certain mitigation measures so that you can make it stable. That's about it. I hope I'm within time. I'm going a little bit fast, but I hope it is clear.
Thank you, Dr. Suresh Kumar. And we have come very, very far from those two famous failures in bridge engineering, Tacoma Bridge, that happened in November 7, 1940. And I recollect, like that the ferry bridge failure, ferry bridge cooling tower failure, though it's a word bridge is there, it was a cooling tower failure, that happened in November 1, 1965, I think, if I'm not mistaken. And both happened in November, incidentally, the Tacoma Bridge failure as well as the ferry bridge cooling tower failure. So as I can see that, like your RWDI and other wind tunnel testing facilities has come far from that, and that too failures really changed the perception of the wind engineering. Basically what I feel is one is turbulence, the another is basically the flutter and galloping. I could see that. So thank you very much for that wonderful presentation of yours, and there are some questions, almost around 9 questions. Before deep diving into these questions, I invite our Alok Bhomik, who has been involved in the design of many of the cable supporting bridges these days in India, including cable stay as well as the extrude bridges, which has been built all over India now. Alok, I think you would like to add on to the excellent presentations which have been made by Professor Prem Krishna and Dr. Suresh Kumar.
I think nothing much to add. Actually, I'm awestruck with the kind of presentation that I hear
Yeah.
from both experts, and of course, I have heard both of them earlier also. Uh, and I think a lot of it, you know, we have deliberated during the preparation of the guideline on cable stayed bridge and extra dose bridges in IRC SP 136, which Professor Prem Krishna talked about. And honestly, these are areas which is future for bridge engineers. Uh, Most of us are not very well conversant with the aerodynamic calculations and aerodynamic, what all we need to take care. I mean, whatever Professor Prem Krishna ji and Dr. Suresh mentioned today, I think majority of us are uninitiated on that. And I think in times to come, we will see more and more of cable stayed bridges and more application of these concepts in the design. And I think that's all from my side. I'm very happy that IAStructE has today, organized this. Special thanks to Dr. Dhawan, who has been instrumental in organizing such lectures. Thank you very much, Dhawan sir.
So with that remarks of Mr. Alok Bhaumik, we come to a very important session. Normally, I enjoy this question and answer session. Basically, it's always highly knowledge, like I get a lot of learnings from this question and answer sessions. And also, as you people are aware, that my motto is to see that all the questions are answered, nothing goes unanswered. With this, I have got one question to myself to Dr. K. Suresh Kumar. Like this, in India, there's a lot of myth. Like that sectional model test may not be adequate to do for the, the bridges. Many of the clients insist for this, like full scale model test. I think, is it? What is your view? What are your views on that, Dr. K. Suresh Kumar? Because I want to hear from you and all the others also who are there in the audience to hear from you.
That's a very good question. See, basic is basic. I think without section model test, jumping into air elastic is not a good idea, because first we have to make sure our test section is stable, and then make a calculated judgment whether you wanted to really go for air elastic or not, full bridge. Most of the time, the air elastic is very important when you have hilly terrains and things like that, because you may have steered flows at odd angles of attack and things like that. So for which I think where air elastic may be making some sense. But in general, like one of the slides which I showed, some of the fundamentals to be done, and without those fundamentals, we shouldn't be moving into air elastic. And air elastic can be, you can take a judgment call at that time. Once you see everything, whether you want to go into air elastic or not, whether you're going to be, from the accuracy point of view, and plus from the cost point of view, and etc. These are not like simple tests. Okay, this is going to cost a lot as well. So unless otherwise you get some benefit out of it, then I think you have to have a discussion at that point. I would leave it there.
Okay, I think that's a very balanced answer you have given. Like that. Anyway, I think let's come to this question and answer.
I'll add to.
Yes,
I'll
yes.
add to
Yeah,
what
go ahead, sir.
Suresh
Yeah,
said.
yeah, Professor Prem Krishna.
See, I think the amount of effort required in a sectional model test compared to a full elastic model test, there is a big ratio of
Very, very
effort
good.
and time and cost. So
Yeah.
therefore, as he said, unless we really need to do a aeroelastic test, we should try to get all the information from the sectional model,
Yes.
which
I
we
would
can do
agree.
more simply compared to the aeroelastic
Yes.
model.
Yeah.
Yes.
But there may be special reasons for doing it.
Yeah.
Aeroelastic test.
Yeah,
Yeah,
yeah.
yeah. Is it not wise to leave that decision to the wind tunnel testing experts rather than like insisting upon in a contract document for that matter.
Yeah,
What do you,
yeah, that is something which is happening not only in most of the time in bridges though, because it comes with a requirement to do aeroelastic right from the beginning.
yes,
So I have seen it recently as well. But like I said, there are special cases where it may require, because in terms of, for instance, when you do section mount test, you're looking at only two frequencies. You're looking at primarily, first torsion mode and maybe first vertical mode. And if you're suspecting that second order mode may have an impact, you can scale the results as well, or you can just change the springs and you can check for the second order modes, okay? So that is all possible with the elastic, but however, the collective effort of all the modes cannot be simulated, right? Because only one at a time. So you'll do second order mode or first order mode and etc. So in elastic, you can get the combined effect of all the modes. So that is one thing. Second thing is, like I said, the overall impact of the terrain and all of those things you can get out of it. However, you have to understand that when you do section model tests and you move into buffeting, in buffeting analysis, everything has been included already. Because in buffeting, you're looking at all the modes, maybe up to 40, 50 modes will be taken care of. So all the impacts of various interactions between the modes and etc., everything has been included in buffeting. So it is not that we are leaving, we are leaving everything, for their elastic. We know that these impacts, and that is why the buffeting is in place, and analytically it will be taken care of, which is probably much easier compared to doing a full error.
thanks, thank you, Dr. Suresh Kumar, for that. And I request all of you to put the questions in question and answer box, because the priority will be given to those. And from the chat box, only if the time permits, I'll be coming to the chat box. That's the reason I think it's better to put. Thank you, Dr. Subramanian, for reminding the others also to put the questions in the question and answer box. And with that, I'll come straight to the questions which is there in the question and answer box. Piyush Santalia's question to, I think perhaps to Professor Prem Krishna, frequency of vibration, if it's exceeding 1 Hertz for cables stay bridges, all modes are coupled. So which mode of vibration should be chosen here? Both of you can take, any one of you can take this question.
Yeah, maybe Dr. Suresh. Yeah.
See, the modes of vibration should be selected based on some other parameters, not just by looking at the coupling of the modes. We should be, first of all, we should be calculating Scruton number. Okay, that is the primary, is very important. So for each frequency or each modes may be coupled. So look at what is the mass participation is happening, mass damping parameter. So once you go through, typically we calculate for all the modes, okay, and we'll see which modes are going to get the least, Scruton number. So our judgment is based on that, mostly based on that. Okay, we look at the Scruton number variations between various modes and then we select accordingly. There's no, again, this is not written in stones and there is no easy way to find out. This is through experience and through judgments. That's all I can say. So, but Scruton number is underlying parameter for sure, because the motion will happen only when you have these numbers are very extremely low.
There's another question from Mr. Paul, Devjyoti Paul. He is asking if the tower is there on top of the building, whether only the tower height should be considered in assessing the wind sensitivity, or entire building. I think if you have to take building plus tower to.
Total.
Yeah, the tower may have higher order modes, when you look at it. The fundamental mode, maybe the entire building is moving, including the tower, but at the higher order modes, the top alone will be moving. So that's what we have been seeing in those cases.
Yeah. Nishi Gupta is asking, I didn't understand this question. What is WT? I don't know.
Oh, WT is a parameter which I think Professor Prem Krishna has shown. in his presentation. This is a Scruton number,
Oh, I see.
including B by D, D by L, and all of those things. You have to multiply and get that number. And if that number is less than 1, then likely you have to do an internal test. So this is written on a paper by our team. So if somebody is interested, I can share the paper.
Yeah. Nishi Gupta is again asking how to create the torsional spring. Maybe in the sectional model he's asking.
Not torsional spring, it is basically springs assembled in a horizontal direction.
Okay.
So you have springs, vertical springs, as well as horizontal springs.
Yeah.
So both of them will create exactly what you're looking for.
So there's a question from Escritorio Bellamino. It's very interesting to, the foreign participants also I'm seeing because of, I think, Dr. K. Suresh Kumar here. And I would like to know if there are some other way to perform sectional model test rather than do it in the labs. I think maybe he's talking about the desktop studies.
Well, I think he may be referring to CFD.
Yes,
yeah, he may be referring to CFD, and CFD is there is a potential, but I think we need to understand that in bridges, unfortunately, there could be moments. So when you have moments, CFD is going to have even greater effort should be put in, because you need to have moving grids, and you need to, it is much more difficult. We do in bridges, CFD on bridges, but that is basically a solid model, and we apply CFD and you can see water shedding, and maybe you can get some coefficients and etc. out of it. But when the bridge started moving, then your grid needs to be moving along with the bridge as well. So things are getting much more complicated. So I would say at this point, this never been explored quite heavily. So we still rely on the test. Once we get some basic parameters from the test, then we utilize and go back to analytically. That is not CFD. We apply stochastic simulation and do the rest of it using stochastic simulation and find out the loads.
Again, Mr. Gupta is asking that, I think it's about the testing procedure. How do we get forces in wind tunnel where load cells are placed? I think
it's a good question. I think in section model tests, we do have load cells, but that is primarily for assessing drag coefficient and lift coefficient and everything. But in vertical vibrations, typically we have lasers. So you can get the dynamics out of that. Once you know the response, maybe you know the rest of it as well. So we do have lasers on both sides, and lasers pointing in different directions for torsion motion as well as for vertical motions.
Yeah. Abel, there are a couple of questions from Abel Korea Kose. Whether buffeting analysis is required for ULS, ultimate limit state design? If so, should it be added in addition to the static wind effects, or is it required for serviceability design and fatigue design only?
As far as I know, most of the time the bridges, I think, still are looking at 100-year load, 120-year load, depending on which country you are in. Okay, depending on the return period. But in states nowadays, everything is ultimate limit state. They go with the 1700-year speed and do ultimate state design. But in places like here and the rest of the countries, they use 50-year, not 50-year, sorry, 100-year, and then they apply the factor of safety for the ultimate limit state. And serviceability is typically low speed, so maybe 50 or even 20, 25-year return period. That's what serviceability is after.
Professor Prem Krishna would like to take this question. This is about this ultimate limit state, whether buffeting has to be added to this static wind load. That's a question here.
Yeah, the buffeting analysis gives you the dynamic response of the bridge.
Yeah. Yes, it gives. Alok, I think you have anything to add to this? Alok is around?
Yeah.
Yeah,
Yeah.
This question is whether buffeting analysis is required for ultimate limit state. If so, should it be added in addition to static wind effects, or is it required for serviceability limit state design and fatigue design only? What
I
is the
think it is.
practice? What is the practice like? Yeah.
No, you see, I have no idea. I cannot answer this question because we have never done that because we are not doing any cable stayed bridge till date.
Okay.
But in extra dose bridges, we generally, do the basic checks, and generally extra dose bridges do pass these, basic checks, and we don't need to really take care of these things. But I think buffeting check is required in the service. It's a serviceability design requirement and a fatigue requirement. I don't think it is an ultimate limit state requirement, but I'm not very sure.
Yeah, Professor Prem Krishna, you would like to add on anything else? I think already Dr. International practice has been explained by Dr. K. Suresh Kumar. And in India, for the cable stay bridges, what are we doing? Like that. It's an interesting question, in fact. Like the buffeting effect is added to the static effects, and after that, whether you do the ultimate limit state check or the serviceability limit state. SLS is the one which normally we do for the extra dose bridges. I am aware of it. I am not sure whether under the ultimate limit state it has to be considered.
For extra dose bridges, normally would you carry out a buffeting analysis?
Only check empirical, whatever the equation which has been given, that we will just check it. And normally the extra dose bridges are not susceptible to this. Buffeting. But in case of cable stay bridges, certainly it is susceptible to buffeting. But once the buffeting is done, I think normally, we will do we not, change the cross section so that the buffeting doesn't occur? Is that not the procedure?
No. Buffeting will occur.
Okay.
Buffeting will occur. Yes.
I think we don't have a clear. Yeah.
You can get a much better idea of the gust factor, for example, from buffeting analysis, compared to all the empirical values that we are going around with.
Yeah. So with the answers which have been given, Mr. Korea Kose, what I understand is it is basically a serviceability limit state. SLS as well as the fatigue limit state. It is not an ultimate limit state. That's what I understand from the discussion so far. But I think it's an interesting question. But this question will be looked into by our codal committee now. Since you have raised it, it's a very interesting question. We'll have to really look into it and see what is to be prescribed in our code. Thank you for asking this
Dr.
question.
Suresh would like to add to this?
Yes.
No, I think what I'm trying to say is that all the bridges that we do, we look at in India, at least I know in buffeting wise, we give always 50 load. We also give serviceability load. Okay. But after that, the factor safety, definitely will be considering factor safety. That means factor safety is more like taking the 100-year load to ultimate limit state. Right? You're just multiplying it, but what I'm saying is that that's the way we have been doing since we don't have 700 or 1700-year speeds in the code. So this is the procedure that we do. So it is, design is considered ultimate only, but serviceability and fatigue and other things obviously for lower return period. So lower return period will be used for fatigue and serviceability.
Yeah, it's an interesting question in, it's a very good question. I think we certainly will look into that. And now PNSS Shastri is asking how to obtain structural damping properties of a bridge deck. I think it is for you, Dr. K. Suresh Kumar. You get into trouble as far as this. What is the critical damping ratio to be considered?
The damping ratio. Okay.
Yes, yeah.
Well, the damping ratio is another area which is, depending on which code you look at it, the ranges are given. Good luck. So, because I'm dealing with buildings also, this depending on the country that you are doing the project, damping ratio is different. Okay, that's the way things, the damping ratio goes. As far as the bridge is concerned, I would say very long span bridges, we consider 0.3% damping most of the time for testing, typically 0.3%. But the ranges that we are doing in India, like of the order of 100 or 200, 300, even 400, they're using around 0.5%. Occasionally, we move into the 0.7% region as well. Okay, and these are all concrete dikes.
Yeah.
And if it is steel dike, then things are even going below actually. So this is something, you see, once, well, what can I say? I mean, if there is any requirement for a damper on a bridge, then you will come to know the exact damming of the bridge, because we will not install any damper without checking the actual damming of the bridge. So we will be exciting the bridge, we will do some on-site monitoring, and then only we'll decide whether what is the damming, extra damming required to arrest the motions. But in all other cases, we typically don't go after this particular thing unless otherwise we were asked to do so. Okay, and these ranges are fairly good ranges, I would say, and we never ever experienced any issues.
Yeah, there is another question from, I think, Mr. Kurio Kose. He seems to have been having a lot of questions as far as the buffeting analysis is concerned. It looks like from
Yes.
this, but this question, I think it may be requiring a lot of time to, I think it may be perhaps another webinar is required. Please explain the process of performing buffeting analysis where
Yes.
correlated wind time histories are applied along the deck and
Yeah.
along pylon to performing buffeting analysis in time domain. Also
Yes.
compare it to simplified equivalent quasi-static load method of buffeting. And I think it's a...
I read that question
Yeah.
and I thought, yes, maybe another webinar.
Yeah, for sure. Yeah. Actually,
Yeah.
these are correlated time series with some coherence is blown against the wind, blown against the bridge. And the bridge elements are modeled like a lambda mass deck. You have the pylons, you have the cables, all the elements are there. And the theory is well written, and you can get the response. And the response, what you get out of the bridge, has been confirmed against the full scale measurements as well, especially in Tackman arrows. We have done it, we have written the paper, we have checked against Tackman arrows as well. Okay, if he is interested, I can send the full paper. There are lots of equations, there's no abundant equations, and you have to solve it. And everything in time domain, obviously. This is not a frequency domain business, everything in time domain. So it's all well written and well calibrated models, so which has been in use.
I think that should satisfy Mr. Koryakose. And Narendra Kopula is asking to Dr. Prem Krishna, possibility of occurrence of torsional wind about pylon vertical axis, plan torsional wind, as this effect is not covered in IRC 136. Kindly share your experience in this aspect. Pylon vertical axis torsion.
Yeah, I get the question. Of course, I have no experience in it, but I think that in a cable stayed bridge, this can be a possibility. Now, depending upon what cables are connected and so on and so forth. And if it is not covered in the code, maybe I said 75 doesn't cover it. It has to be something which has to be thought about.
Dr. Suresh Kumar, you would like to add on?
Well, I think pylon at its construction stage, sways are more important than torsion for sure. Okay, because torsion will be extremely stiff in torsion, most of the time sways. But once it is all construction completed, then this torsional thing will come into picture. However, at that time, I mean, the stiffness of the different pylons and cables and deck, everything will come into picture. So I can't say much more than this, except as far as the stability of the bridge is concerned, we want the torsional mode to be far away from the vertical vibration of the bridge. Okay, that is something that we look at it all the time. We don't want these things to be very close so that it will get into But that particular motion, what I am talking about, is primarily the torsion motion of the bridge is primarily deck. It is not really the pylon. Okay, it is primarily the deck.
Yeah, I agree.
Yeah,
Of course, in the deck, yes, we are concerned
yeah,
about the
yeah.
torsion. Very much.
At the outset, it looks like, the pylon is not sort of susceptible to torsion, like that at the outset. That's the
Yes.
reason I think perhaps it's not covered in our IRC 136. I don't know whether it has been covered anywhere else.
I don't know
I
about
don't
it.
think
But,
so.
but I mean, as you say, perhaps it is not going to be a significant thing for design.
Yeah. And Abel Curio Kose again is asking, you had mentioned during the presentation that aerodynamic derivative functions will be used in buffeting analysis. Kindly explain how it will be used in buffeting analysis.
Well, you have to look at the equations, okay? Because simple dynamic equations where you'll have one side the motion induced forces.
Yes.
The other side will have mass, damping, stiffness, and etc. These are simple equations. You can write two equations, one for vertical motion-induced oscillations, the other one for torsional motion-induced oscillations. So in each one of these forces on the right side, that is motion-induced, where these four parameters will come, H1 star to H4 star and A1 star to A4 star. And this, if it is negative, it is good for you. If it is positive, it is not good for you because it will negate your damping and negate your stiffness. How do you find all these things during the testing? You can excite the bridge, you can let it die, and you get those traces, and you have to do system identification techniques. You have to find out all of these parameters. Okay, and that is a typical process. But you have to get the traces from the tunnel itself, and then you can do the rest in a computer, and you can get those parameters. And as soon as you have those graphs, whether you are getting into any kind of trouble or not, because you will have the velocity, reduced velocity at the bottom. And as far as it passes the reduced velocity that you're looking for, then you don't have an issue. So, and these parameters will be utilized in the buffeting analysis, basically to solve those equations and get you the load. So I think if you are interested, the best thing is to refer the paper because it's not something very easy to explain.
Yeah.
Yeah.
I'm going to.
I can say that there's a lot of literature
Yes.
on Plateau derivatives,
Yes.
from the tunnel. A lot of literature.
Yeah. I'm going to take the question up to 7 o'clock because Dr. Suresh Kumar had requested
Yeah,
that
had to be leaving. Yes,
that he would be leaving by 6:30, but we have already extended the period. But we'll try to answer as many questions as possible by 7. I think Dr. Suresh, I think you can leave at 7. And my request is that. Okay.
Yeah, sure.
Yeah. So, what are the devices available to capture vibration in wind tunnel to lab except laser? I think that
there are accelerometers, gauges.
There are so many. Yes,
accelerometers are very common. Okay, you can put it at the cables at the top of your pylon. Those are particularly used in the aeroelastic test. Okay, especially accelerometers. And then in aeroelastic test too, we'll have lasers from underneath to check the vibration of the deck. Because if you have the vibration of the deck at multiple points, you have the load actually. You'll get load out of it. You can back calculate from the deflections what will be the load. So that's how we'll derive the load actually sometimes. You can also have gauges and other things. So these are typical measurement techniques.
So Mr. Shastri is asking, I think it's a obvious question, it looks like, can CFD be a good starting point before doing physical models tests? I think it looks like, right? Suresh Kumar,
yeah, only for non-moving stuff. Yeah, we will come to know very large water shedding happening, whether the test section need to be changed potentially. In those cases, like I said, I mean, in my talk, I said desktop assessment. And the assessment will come along with the CFD. Okay, at the assessment stage, we'll also use some CFD to figure out whether any issue anticipated. So that is the only time we use CFD. Afterwards, there's no CFD.
So there's an interesting question for Mr.
It's an FIR, first information report.
Interesting question from Mr. Telanga. I think it's for you, Dr. Prem Krishna. He says that as per IRC 136, you are using for the dynamic effects 3-second gust average, whereas the other international codes use the 10-minute mean velocity. And is that okay? I don't think so. I think you said mean hourly for the dynamic, right?
Mean hourly, yeah.
Yes, not the gust, but yes. So the second question is, Mr. Sunai, do we have wind tunnel testing facilities in India? What would be the cost towards wind tunnel testing for a typical long span bridge? I think there are many facilities for the wind tunnel testing. And I said that the RWDI also has established under the stewardship of Dr. Suresh Kumar in Trivandrum also. I think they have been doing a lot of wind tunnel testing. I don't know as far as the cost is concerned. Typical long span bridge, what will be the cost? I think it depends upon sectional model test.
Yeah, the complications and everything. So we cannot generalize it.
It cannot generalize. Mr. Gupta is again asking, in our wind tunnel lab, do we have one load cell placed on the ground for buildings? Can we do testing on a section model of a bridge on that load cell? I think it's a nitty-gritty of the procedure of the load testing itself. I don't know. I think Mr. Gupta, you'll have to have a separate dialogue with Dr. Suresh Kumar here. Would you like to take up that question, Suresh Kumar?
What I was hearing is building, or is it bridges or building?
In our wind tunnel lab, we have one load cell placed on ground, particularly for buildings. Can we do testing on section model of bridge on the load cell?
I doubt it, because we are talking about both sides.
Because you have to have the load cells on the sides.
Yeah, sides we can have it. Yeah, sides we can have it.
If you have one at the bottom, I don't think you can use that.
Yeah, exactly. Yeah.
So the gust factor 2 is used in IRC 6 up to the span of 150 meters. Generally, the cable stage bit does this gust factor work due to be much higher than 2 or lower? I think 2 is the maximum we are using.
2 is the gust factor. 2 is the minimum, I think.
2 is the minimum you are using.
Minimum. 2 is the minimum. And I would say, okay, that is good for estimating things, but one should go for the buffeting analysis to get a better idea of the aerodynamic behavior.
So, Atra is asking a question whether for the transmission tower, whether the wind tunnel testing is required. I think.
Well, I don't see. This is out of the scope at this point. It may require, it may not require. So depending on, because typically these towers are not being tested. However, there are a lot of failures, and those failures are caused by thunderstorms, and so it's totally a different topic, and probably
yes. I will take some interesting questions before Dr. Suresh Kumar leaves. He's got another 3-4 minutes. When is the full aeroelastic test required to be done, and up to buffeting analysis good enough? What is the decision-making parameter here?
That is very difficult to answer.
I think
I already kind of told.
You have already answered that.
Yeah, this is a judgment call by the consultant. He has to be absolutely. We will never suggest anything which is not required. Actually, we'll be the first one saying don't do it. So I think we have to make that judgment call once the initial stuff is over, whether it has to go through that or not.
I don't know what is this question. Ashish Sarode is asking, are there any guidelines for wind tunnel test and light loads for the safety of the running traffic? I don't think so.
No, I don't suppose so.
I
don't think we have any guidelines on that.
For that, yes. And Mr. Gupta is asking, what is the significance of frequency ratio?
Oh, frequency ratio.
Yes.
Okay, the frequency ratio we are talking about is torsional to vertical. If they are very close, then there is a chance of flutter. So typically we say that, okay, make the torsion at least 2 times the vertical away so that you may not get into flutter situation. So these are some checks that typically we do at the beginning.
Yeah.
So, yeah.
Mr. Gupta's question to Dr. Suresh Kumar, how do we calculate the stiffness of spring for aeroelastic testing?
The spring is, I think the spring comes with its own stiffness because we buy a bunch of springs and we'll keep it. That's what we do. We have all kinds of ranges in our lab. So we look at what is the requirement based on our calculation, based on the frequency of the bridge, and we'll decide which spring to be used for the test. So it is as simple as that. We don't calculate and go for a purchase because we don't have time. So we'll have all the collections with us.
So I think that's only a couple of questions. I'll finish it off. Mr. Jafar is asking if the bridge is in the leeward side, same design principles apply. That's what I understand from the question. It has to be done, no? Even whether it's a leeward or windward, you'll have to put both the decks together and do the sectional model test as Dr. Suresh Kumar explained, and we'll have to find out the results, whether it's susceptible to the wind dynamics. Am I right, Dr. Suresh Kumar?
Yeah, sometimes there are metro bridges and other bridges are there when a new bridge comes. So we have to test from both directions because we don't know which one is going to be governing. So in such cases, we'll have those bridge on the side.
So the last question, Gaurav Gai, I think it's not related to basically the wind engineering, but he says, why are we not using orthotropic steel deck in India? Basically, it's going to be expensive. That is the reason we do not use that. And also the spans beyond perhaps, like 500 meter for the cable, that too for the suspension bridges, as far as the cable stayed bridges, to reduce the weight of the superstructure, normally orthotropic deck is used, Up to 500 meter steel composite with the RCC decks always becomes economical. So with this, Dr. Suresh Kumar, thanks for extending your time for half an hour, and we are privileged to have you here. It was a wonderful. I think you have answered most of the questions which have been raised by our esteemed participants here. I think they're also very learned participants. You can make out that. Thank you very much, Professor Prem Krishna. I don't know how to thank you.
Thanks, everybody.
Basically, Bhishma Pitamaha was a word which I used as a compliment, and you told me once after finishing that civil infrastructure document on sustainability, you want to hang up your boots. We will not allow it. We will not allow it. You will not be hanging up your boots. With this, I'll give back this podium back to Dr. S.K. Dhawan.
Thank you very much.
Both these speakers are renowned, eminent engineers, and then they share their knowledge and experience. And I'm sure that the listeners have definitely gained confidence and knowledge in knowing, and now they can have more interest and then read further the journals as well as the codes to know more and more. So, friends, thank you for listening and spending time to listen to great eminent two speakers. The next month, the next topic, and the next speaker. So wait till that, and we conclude the session. And,
thank you, sir.
Thank you.
Dr. Dhawan.
Thank you.
Thanks, sir.
Thank you, Suresh, for
thank you, sir.
to my request.
No problem, sir. Thank you. Anytime. Thank you.
So with that, we are concluding today. Thank you very much.
Okay.
Thank you all.
Thanks, everybody.
Thank you.